Okay, so welcome to our last seminar for this rather interesting year. We should have a quite excellent talk by Craig, so it's a total honor to end with Craig. And so take it away, Craig.
Yeah, thank you for that very kind introduction. I hope that I can live up to the expectations that you just set. Let's just see. So I hope you can see my screen, and I hope you can also see my mouse moving. I'm only using one screen today, so I won't be able to see if you have any questions. So if you have any questions, please just shout them at me, and I will try and answer. I encourage as many questions as possible. So I'm going to tell you about some recent work on 61,0 SCFTs and their compactifications to 4 dimensions, and then comparisons with the more developed story of which is called class S. I'm sure many of you know this. So this will be based on a paper which we're hoping to put on the archive next week with Florent Baume and Monica Kang. So you should look out for that in the near future. So this is a seminar series on QFT and geometry. And this slide is there for 2 reasons. The first reason is that I need to remind myself that I want to say something deep, as you were saying. So what I just want to say is that this seminar series has been very sort of helpful and invigorating throughout a year that's been challenging at times. And I think it's kept sort of a sense of sort of community ongoing. And so I think we're all very grateful to the organizers for taking on that extra work and organizing it. So I just wanted to say that as the final seminar of the year. I also want to say that even when we talk about QFT in geometry, often the best way to take advantage of geometry is to have extra structure in your quantum field theory. So going beyond simply unitarity or whatever you may assume in the sort of basic definitions of quantum field theory, and including some extra structure. Now, these extra structures can be things like supersymmetry or conformal symmetry. Particularly, I will focus today on superconformal symmetry as the extra structure in my quantum field theory. And once you assume these extra symmetries, you get a lot of extra avenues to attack physical problems via geometry. So I will focus on superconformal symmetry today, as you can tell from my title. And I will also focus on 6 dimensions. So why do I want to focus on 6 dimensions? 6 dimensions is the maximum dimension, which allows you to have a quantum field theory that has superconformal symmetry. This is an old result by Nahm from, I think, the 70s. And there is sort of one theory that has the maximum amount of supersymmetry in 6 dimensions. It's called the 6-dimensional 2,0 theory. It has 16 supercharges. And these theories are parameterized by a choice of ADE gauge algebra. It's not really a gauge algebra of the theory, but it's an ADE classification of these kinds of theories. So that means that there's 2 infinite series corresponding to the A and D series, and then there are 3 exceptional cases corresponding to the E6, E7, E8 gauge theories. And we'll see why that's important later on. So what can we learn from understanding these 60 superconformal field theories? Well, one avenue which has had a lot of development over the last at least 10 years has been to consider compactifications of the 62,0 and ask, what does that tell you about lower dimensional theories? And so there's been great progress, for example, looking at the AGT correspondence or the 3D correspondence, where you learn about interesting relation dimensional theories. I'm not going to talk about those 2 things today, but they're a good thing to keep in mind whenever we're talking about sort of 60 origins and where we might be able to use that. So a very, very simple example of where using geometry of a 6-dimensional compactification tells you sort of something very helpful about a lower dimensional theory is in 4-dimensional n=4 super Yang-Mills. So super Yang-Mills, or n=4 super Yang-Mills specifically, has a strong weak duality. It's an SL2Z symmetry, or SL2Z duality, I should say, which maps strongly coupled sectors of the theory and weakly coupled sectors of the theory into each other. So essentially, it does this by being one of the generators of the symmetry is an inversion of the coupling constant. So you can understand why this is a very hard symmetry to analyze and to provide evidence for, because the way you would do that is you would compute something at strong coupling, and you would compute something at weak coupling, and you would compare them. But almost by definition, computing something at strong coupling is challenging. However, if you were to start from the 6-dimensional point of view, then you compactify it on a T2 to get 4D n = 4. And that T2 has an SL2Z symmetry, which transforms the complex structure parameter of the torus. That's really a geometric symmetry. And that symmetry itself is what gives rise to the SL2Z symmetry of n = 4 super Yang-Mills. So we've taken some complicated, sort of strong, weak duality that's hard to access in 4 dimensions, and we've turned it into a manifest geometric symmetry in 6 dimensions. So already you can see that from 6 dimensions, you learn things about the theory which may have been very difficult. So I'm going to talk about an extension of this in the talk today. And I want to give you sort of a quick overview before we delve into the details. So instead of doing n = 4 super Yang-Mills, you could start with the 62,0 superconformal field theory again and compactify it on a Riemann surface. And generally speaking, you end up with a 4-dimensional n = 2 theory. So this gives a set of theories associated to Riemann surfaces. However, you might ask, there are also 6-dimensional superconformal field theories with 8 supercharges. They're called the 1,0 SCFTs. And compactifying these theories on a torus will also give you a 4D n = 2 SCFT. So perhaps an interesting question just in its own right is there overlap between these two sets? Are there theories which have an origin as a 62,0 theory on a Riemann surface and as a 61,0 theory on a torus? So this is an interesting question. Just in theory, why do certain theories have 2 parents in this way and why not? However, there's also a very practical reason to want to understand this question, which is that if you have 2 different 6D origins of a theory, then you can access different physical data in 4D. For example, in this picture here, you may have physical data in 4D which depends on this choice of Riemann surface. But the Riemann surface does not appear over here. So data which might be obvious over here can be hidden in the construction over here and vice versa. So having many different origins of the theory can give you sort of easier way to access different pieces of data of the theory. Okay, so what might you be interested in accessing? So the physical data of a 4D n = 2 SCFT, well, they have various pieces of data, and here are 3. So they have some central charges. So the central charges are essentially a measure of the degrees of freedom of the theory. So if the theory was a weakly coupled theory, then these quantities NV and NH are simply the number of vector and hypermultiplets in the theory. And now you understand why I say it's like counting the degrees of freedom. However, even in a strongly coupled theory, these are quantities which exist and can be computed. Another feature of a field theory can be its flavor symmetry or global symmetry group. Yes, and this global symmetry group also has an associated central charge, which is essentially just proportional to the 2-point function of the flavor currents. So one way you might want to check if 2 theories can possibly be the same is if this particular data is the same. So if you yes.
May I ask a question?
Yes, please do.
I wonder, that let's say that in 4D theory, you can consider weak coupling, right? For example, so an n equal 4, you can deal with weak coupling. In your original six-dimensional theory, I'm not sure, you know, so you thought about degrees of freedom, whatever, so you can consider this in normal way. But in six-dimensional theory, it's kind of, technically it looks like non-normalizable, right? So the coupling is dimensionful, right? So to what extent you can consider this as a weak coupling in original six dimension?
So I will never talk about anything like weak coupling in 6 dimensions. So the 6-dimensional theory is just, it's some super conformal interacting thing. And there are certain pieces of data that you can understand about that theory. In particular, you can understand the anomalies of that theory. And that's the data that we'll use to determine the data of the 4D theories after compactifying.
Right, so we don't need... So in 6 dimension, you do not have this picture of degrees of freedom, or, you know, explicitly whatever, right? Because I do not see that. Yeah, I see. So in this way, it's a little bit symbolic, right? 6 dimensional theory, in the sense of your explicit the explicit construction of 6 dimension, right? In difference with 4 dimension.
Exactly. So what I am going to tell you is eventually that you can compute what the 4-dimensional central charge is, which in 4 dimensions measure the degrees of freedom. You can compute those from these 2 different 6D origins.
Okay, I'm sorry to interrupt. Thank you.
Yeah.
I have a question also.
You still, in 6 dimensions, you still have Weil anomaly coefficients, which are just another way of rewriting NH and NV. In fact, you have more Weil anomaly coefficients in 6 dimensions. Having 4, and in at least in the 1-0 theories, you have flavor central charges. I mean, so you have similar data in 6 dimensions to what he's going to compute here. So.
Yes, you absolutely. I mean, you have similar quantities, and you also have quantities which you know, decrease along flows in 6-dimensional theories and so on, that look like they correspond to kind of A-type quantities and so on. So in 6D you have similar quantities, but we're not using them at any stage here. We will use basically purely the anomaly data of the 6D theory.
I have a question. What about comparing the conformal manifold?
Okay, good point. So you might, for example, have a problem that I've said 2 theories can be the same if they have the same flavor symmetry. And you might say, well, if you look at a different point on the conformal manifold, they have different flavor symmetries, etc., etc. So
that's actually not where I was going. I mean, it seemed to me that, is it clear from the 6D10 point of view how you get the conformal manifold, which is the Teichmuller space? Riemann surface C?
No. So from the 6D 1,0 theory, it's not clear where you get the conformal manifold from. The best thing I can say is you write down the geometry, you construct the mirror geometry, and then you can see the Riemann surface of the class S construction there. But that's one piece of data that I don't know how to see from the 6D point of view, 1,0 point of view.
So I have one more question on this. In class S, we know of examples of theories which are distinct SCFTs, but have the same Weil anomaly coefficients, flavor symmetries, and flavor central charges.
Absolutely. So in the specific class of examples I will talk about today, I do not believe there is any theory that has all 3 of these being the same but are distinct theories.
Well, what I'm asking is sort of, how do you know?
Okay, so good. So let me just say this now, then I'll come back to it later. So you might indeed ask the question of, just because you match sort of this set of discrete data between sort of a theory coming from 2,0 and a theory coming from 1,0, that doesn't.
But even now, I'm saying 2 theories coming from 2,0, 2 theories in class S. with the same set of data listed on this slide,
Yes.
it can nonetheless be distinct. I mean, are nonetheless distinct.
Absolutely. Okay, so what we will compare will be the three punctured spheres. And in fact, we will compare the three punctured spheres where one of the punctures is a simple puncture. Now, you can have, for example, different sets of punctures that give the same set of data here. However, I believe that in that set of objects, in fact, I believe you showed this at least for these theories. I believe in your Tinkertoy papers that these three punctured spheres, these correspond to the set of things, and they are distinct or not. So I guess the point I'm trying to make is that if you choose the sphere and the three punctures, and one of the punctures is a simple puncture, then this accident that you're talking about does not occur in the examples that we look at.
Well, maybe. You should probably go ahead.
I mean, I can show you the tables in the end, and it seems it doesn't happen. But I agree, this is something that we were concerned about.
Related to Greg's question, so I guess you just said you're only comparing spheres so far, but could you presumably have an understanding where, you know, the parameters of the genus and the number of punctures itself would come from the 1-0 theory?
So one thing that you find is that when you look at higher genus and higher number of punctures, it becomes more challenging to find convincing overlaps between class S and the 1,0 theories on a T2. In particular, if you consider like class S theories with their with say a genus dependence, and you try and match that genus to some parameter on the 1,0 compactification side, let's call that n, then it's very hard to find a convincing relation between G and n. So one of the emphases I want to make is that there seems to be a significant but very specific set of theories which have realizations from both of these points of view.
So related to this question, so are you going to be able to do more than just linear quivers?
In 40 or in 60?
In 40.
So all I will talk about today is three punctured spheres.
Okay, so that you can glue to make linear quivers. Okay.
That's right. That's right. I don't want to make a commitment on other things right now because it's at the moment quite unclear.
Okay, thank you.
Yeah. Okay. So two theories can be the same theory if they have similar physical data, is what I wanted to emphasize. So the first thing I have to tell you about is the first side of this little triangle here, which is the most developed side, I would say. And this is the class S construction. So this goes back to, I think, 2008 or 2009 by Gaudo and papers by Gaudo-Mornitsky. And the idea behind this construction is that you start with a 6D 2,0 theory that we talked about, and you compactify it on an n-punctured genus G Riemann surface, which I've schematically drawn here. When you do this, you get a 4D n equals 2 superconformal field theory. And the geometric properties of this punctured Riemann surface, these tell you about the physics of the superconformal field theory. This is our wonderful relationship between geometry and physics that this seminar series is built around. So how do you get 4D physics from this? So this has been sort of very well studied. The central charges are given as some combinations of essentially a global piece that depends on the genus here, and the type of algebra describing the 6D theory. If you can't tell the difference between my G and my math frac G, that's not surprising, but I think context will suffice. And then there is a local contribution from each of the punctures, which I've labeled as OI. So this is NV and NH, the central charges. There is a flavor symmetry. And that flavor symmetry is formed by taking the flavor symmetry of each of the punctures. However, this is not necessarily a complete story because the flavor symmetry can in fact be enhanced beyond this, as I will discuss a little bit later. And then there is a duality group, and the conformal manifold are also understood in terms of the geometry of this Riemann surface.
Sorry, I thought the duality group was the Teichmüller modular group preserving the identities of punctures.
Yes.
Right.
So,
I mean, only a quotient of that will map to SPT.
Right. Right. Absolutely. Yes. Yes. I just wanted to give the simple one that reduces to the torus case that we talked about in n equals 4. But yeah, you're absolutely right. It's the Teichmüller space. Yes. Okay. So far I've talked about genus GN punctured Riemann surfaces, but these can be decomposed geometrically via what's called a pair-pants decomposition, where you split each such Riemann surface into a set of 3 puncture spheres and you glue them together along the punctures. So if you want to understand the space of class S theories, a good place to start is to understand the 3 puncture spheres, and then, as Ibu was just alluding to, you can start gluing these together to form more complicated geometries and thus more complicated 4D theories. So these 3 punctured spheres, they go by the names of Tinker Toys, and has been sort of studied in a lot of detail over the last 10 years or so by Chalcatana, Dissler, Trim, and Zhu in some different configurations. Okay, so the key point here is that you can have different kinds of punctures. And here's just an example that I've taken from one of these papers of the different kind of punctures that are possible when the 2,0 theory has associated algebra E6. So there can be quite a few of these, and of course 3 punctured spheres involve taking 3 of them. So you can see that this set of things can grow pretty large. But these have all been sort of documented in great detail in the sequence of papers that I described here. So we see we get a large number of 4D n equals 2 theories corresponding to 3 punctured spheres. So for us, that was a great place to start. It's also a great place to start because these theories have no exactly marginal couplings. So you can start thinking that you should match the flavor symmetries on both sides perfectly. Okay. So what I told you was that if I replace CGN with a 3 punctured sphere, you get a lot of theories down here. So you see that the dependence is mostly, you could say, the variety mostly depends on the choice of punctures in the 3 punctured sphere. You have a very limited set of choices up here. It's just an AVE classification, but you have many choices here. However, if I now look at this other side, here I'm doing a T2 compactification, and I'm not doing a funny T2 compactification with flux and blah, blah, blah. I'm doing really the most basic thing you can think of. So any variety that comes from here must come from the set of 61,0 SCFTs that you start with. Well, how much variety is there in that set of things? It turns out there is a lot. So if you have a 2,0 theory in 60, you have an ADE classification, that's 2 infinite series, 3 sporadics. If you extend to look at 1,0 theories, you find a lot more theories. So you find about 100,000 infinite series, and there's around 50,000 sporadics. These numbers are more of an order of magnitude kind of numbers, but they're about right. So that's a lot more SCFTs in 60 to play with. Okay. So if I just go back to this picture, I just want to first of all tell you what is already known about relations from over here and to over here. So if you take the 62,0 theory of type G and you compactify it on a sphere with 2 full and 1 simple puncture, then this is the same thing as what's called GG conformal matter, which is just the theory of a single M5 brane probing an ADE singularity, and then compactify that on a T2. So this set of examples was worked out in this paper of Omori, Shimizu, Tachikawa, and Yonekura. And a few more examples were worked out. Different kinds of conformal matter were worked out in this paper of Chalcatana, Dissler, Tremonzu. Okay, so that's what was known before. And what we will see is that every genus 0 3-punctured Riemann surface, where one of the punctures is a simple puncture, all of these 4D n equals 2 theories can also be obtained by taking a 61,0 theory and compactifying on a T2. So the trick is going to be determining what these 61,0 SCFTs actually are. And this is sort of approximately 300 or so theories.
Why do you need a simple puncture?
So I don't have a convincing argument for this. The sort of vague moral argument is that you think of well, actually, I will give you the argument on the next slide because I think I can explain it sort of clearly there.
But is the claim going to be that for 3 generic punctures there won't be a 1-0 viewpoint?
So I won't make the claim that it does not exist. So you can check and you can see if there exists a theory, and sometimes if you look at the central charges and so on, it looks like there could exist one. But I think that's not strong enough to really claim that those are the same theory if you just have sort of a handful of relatively sort of random, unordered examples. So the key point I want to make is that if we restrict to assuming one of the punctures is a simple puncture, then we don't just see that you get a set of things with these central charges and a set of things with these central charges. But if you have 2 class S theories, which are related by what you might call a Coulomb branch deformation, then their 61,0 origins are also related by a complex structure deformation in their geometry, or a Higgs branch flow in 6D language. So the sort of the point why I think this is more convincing than just matching examples is that you also match the structure of the renormalization group flows amongst the different theories, which we know from both the class S point of view and from the 61,0 point of view.
A question to this. So is the need for just having the simple puncture, does it follow from the fact that the 6D theories that you construct themselves have some linear structure where you have some n boxes that you can sort of Higgs down, and then if in 4D is a theory with the simple puncture that admits such a structure? Is it just that, or is there something?
So I believe that's the reason. So for example, if you asked me to come up with a 6D theory, which corresponds to, say, 3 full punctures, so it would have a E6 cubed flavor symmetry, it's very hard to think of, well, I wouldn't say it definitively, but I don't think that such a 6D SCFT with that E6 cubed flavor structure exists because of this kind of linear structure that you're talking about.
Okay, good. Yeah, I think that probably answers the correct question.
Yeah,
I mean, another way of, I think, saying what you just said is you could start with the 3 punctured sphere that corresponds to the conformal matter and start doing partial closures of the punctures.
Yeah, that's right. That's where the linear structure is.
Right, and that's your linear structure. But the point is, you started with something with 1 simple puncture and 2 full punctures. So the simple puncture you can't do anything with, but you can start partially closing the full punctures.
Yes. Yes. Precisely.
Craig, I have one question. You said that theories with 2 maximal punctures and 1 minimal correspond to toric compactification of conformal matter. So what corresponds to compactification of, say, 3 trinion when the group is A-type?
two max. Oh, so okay. So in A type, it's kind of boring because in 60, the theory you're considering is essentially just a free bifundamental hypermultiplet.
I see. Okay. So what?
Yeah.
That's okay. Thanks.
That's not so exciting. Okay. Good. So just to recap, how we match these theories is by comparing their central charges, their flavor symmetries, flavor central charges, and then that they match on the space of deformations or renormalization group flows or moduli space or however you want to call it. So what do we need to know? From the 1, 0 side, we need to know what kind of 1, 0 SCFTs exist, because as I said, all of the variety on that side of things comes from the 61, 0 theories. What are their flavor symmetries? And then to compute the central charges, we'll need to know what the anomalies of those theories are. So this is what I'm now going to tell you. Okay, so how do you build a 60 SCFT? So a 60 SCFT is associated to a non-compact elliptically fibered Calabi-Yau threefold, where you have a set of curves in the base, which are just complex projective space. They're compact, and they have to intersect in each other in a negative definite intersection matrix. So the reason for the negative definiteness is that you want to have a conformal field theory, and in a conformal field theory, you need to have no scales in your theory by definition. And this condition on the negative definiteness of the intersection matrix is essentially what tells you that you can simultaneously shrink all of the curves to 0 volume and thus end up with a geometry, which is now at the origin of the tensor branch, where you have no scales and have a chance of conformal symmetry. Okay.
Craig,
so in addition,
there's a question
yes.
in the chat.
Let me read. The generic punctures PP2 that you take, are they restricted to untwisted? So you can consider twisted punctures, but I will only consider untwisted punctures. Twisted punctures involve some extra subtleties to do with also twisting on the 61, 0 side that I don't want to go into yet. Thank you. Okay, so each curve can have this singular fiber of the elliptic fibration over it, and that can give you an algebra over the curve. So from now on, we're just going to really write curves, algebras. This is a picture of 60 SCFTs with 8 supercharges that has been developed sort of since 2015. There's been many papers, but these are sort of the two defining ones by Heckman, Morrison, Vaffa, and Heckman, Morrison, Rodelius, Vaffa. So let me give you an example. Try and make this as sort of straightforward as possible. I can take 3 curves, have them intersect in a line like this. And I can choose their self-intersections to be -1, -3, -1. And then you see the intersection matrix looks like this. And it's easy to look at this intersection matrix and see that it is negative definiteness. Negative definite. And we're going to invent a shorthand notation for this kind of configuration, which we'll just write the negative of the self-intersection number, because we don't need the minus signs. And then we'll write the algebras over it. So this curve configuration, we would just write as 1, 3, 1 with an SU3 over the -3 curve. Okay, but you can't quite do everything. You need negative definiteness, as I said, to end up with a conformal field theory. But there are also a variety of gluing conditions on the elliptic fiber that you need to worry about. So the way to glue these building blocks together is that you have some basic building blocks, which are called the non-Higgsable clusters. These I've drawn here. They can be either these specific examples, or else they can be ADE Lie algebra, ADE Dynkin diagrams formed out of intersecting -2 curves. So this is all you can do. You start with these things, and then you glue them together by -1 curves. A -1 curve, if it's just on its own, would be associated to the 61, 0 SCFT known as the E string, which you can think of as having M5 branes probe and M9 wall. Okay. And one more thing you can do to build these theories is that if you have a fragment that looks like a -n curve with an algebra G over it, you can increase the rank of that algebra, or at least increase it to some superalgebra G prime. And you can do this sometimes, as I will explain in just a moment. Okay. So the gluing condition tells you that when you glue two non-Higgsable clusters together, remember these things N and M must come from our list that I just gave here. I can only glue them together if the sum of G and H sits inside of E8. So the reason for this is that this property involves gauging a subalgebra of the E8 flavor symmetry of the E string. So of course you can only do that if it sits inside of E8. And furthermore, anomaly cancellation, so gauge anomaly cancellation, so consistency of the theory, tells you that for each curve with a gauge algebra over it, the number and type of hypermultiplets transforming under that gauge algebra is fixed. So for example, if you write down a -1 curve with an SU2 gauge algebra, then you're required to have 10 fundamental hypermultiplets to cancel the anomaly. Okay, so when you're building superconformal field theories in this way, you see the same structures coming up over and over and over again. And when you see that, it's good to give it a name. So these are sort of some of the structures that come up very often, and they're called minimal conformal matter. And they were originally studied in this paper by Del Zotto, Heckman, Tomasello, and Vafa. And you see they're associated to sort of DD, E6, E6, E7, E7, E8, E8. And these are the flavor symmetries of these particular 60 SCFTs. You might wonder why there's no SU or AA type. And the reason for that is that 60 theory is just a free bifundamental hypermultiplet, and that's not an interacting superconformal field theory. So these theories, they behave like a strongly coupled analog of a bifundamental hypermultiplet. Good. So I've told you now something about how you build 60 SCFTs, and now we want to start asking about the properties that we're interested in. So what are the flavor symmetries of 60 SCFTs? So there are two origins. They can be what I'm either calling E-string flavor or what's sometimes known as classical flavor. And I will explain these two concepts in turn. So string flavor occurs when you glue two things together by a -1 curve. So I told you you had to choose a subalgebra G plus A of E8, and you can only glue things which are a subalgebra. So once you've fixed this embedding, there can be some leftover group that commutes with G plus H inside of E. And in that case, this commuting subgroup is a flavor algebra of the theory. So one example of this is our old friend, 131 with SU3 in the middle. So you can see you have an E string here. And on one side, you have an SU3. And what is the commutant inside of E8 of it? The commutant of SU3 inside of E8, well, it's E6. So you have an E6 associated to what was originally the E8 of the E string here, and an E6 associated to what was originally the E8 of the E string here. So that's one way of getting flavor symmetry. The other way is a little bit more obvious, which is if you have a theory with 8 supercharges and you have n hypermultiplets transforming in a particular representation of some gauge algebra, then you have a flavor symmetry group which just rotates those hypermultiplets into each other. And what particular rotation group this is depends on the reality of the representation of choice. So you can have SUN if R is complex, SPN if R is real, or SO2N if R is pseudo-real. So one subtlety is that if R is pseudo-real, you can have half hypers, in which case N can be a half integer, but this is still well-defined. So let me just jump back to the example that we just showed, which is 1SU2. We said it had 10 fundamental hypermultiplets, which means, so since the 2 of SU2 is pseudo-real, you have an SO20 flavor symmetry that rotates those hypermultiplets. So using this procedure, if I hand you a configuration of curves and algebras, you can just roll through and determine what the flavor symmetries are. But maybe that's worrisome. Maybe you're worried, do these flavor symmetries really persist at the origin of the tensor branch? Are they really flavor symmetries of the superconformal field theory? or are they flavor symmetries of the theory on the tensor branch that get broken as you go to the origin? In a paper by Bertolini, Merckx, and Morrison, they studied what happens in the geometry. So in the full elliptic Calabi-Yau geometry that I told you about earlier, and looked at what kind of singular fibers can intersect what kinds of curves and so on. In some cases, it looks like the flavor symmetry may not exist, but it's not entirely clear from the geometric point of view. So one thing that we find is that if you were to compactify these theories and compare them with class S, then you would find flavor symmetries, which are exactly the flavor symmetries that I just described. So this gives some evidence that even though these flavor symmetries are not appearing so obviously in the geometry, they're probably hidden rather than broken. So one reason they may not appear in the geometry is just they're broken, they're not really symmetries. But since the theories of class S, which we compare to, seem to have those symmetry groups, then it makes sense to us that you would expect them to be there. And then that raises the question of how are these hidden in the geometry, if they're hidden in the geometry? And that's something which I think is certainly interesting to explore.
Craig, do you claim that always the symmetries on the tensor branch are the symmetries of the fixed point?
So there's one sort of family of counterexamples to this, which is if you take the SO8, or if you take an SU2 gauge algebra with 8 fundamental flavors, then the symmetry is SO7 instead of SO8 at the origin of the tensor branch. But this we build in just by sort of, that one is like a special case. And that gives you a bunch of sort of derivative special cases to do with if you have less than 8 fundamentals of SU2.
Right. Okay.
But as far as I know, those are the only known exceptions. And from what we find, also from comparing with class S, we find that's the only exception that ever comes up.
Okay, thank you.
Yeah. Good, thank you, yes. Okay, so a simple example of this is if I take this curve configuration, 1, 2, 2, 3, 1, 3, some algebras here, how do I compute the flavor symmetry? Well, I have an E string here, and the commutant of the -1 curve, well, there's nothing there. So the commutant of nothing in E8 is E8, so I have an E8 flavor symmetry here. Here, I have an E string, I have 2 G2s. Okay, fun question. What is the commutant of G2 squared inside of E8? That's not a common one, but it's in fact SU2, but it's a funny SU2 because it has embedding index 8, and that will be important later. And over here, anomaly cancellation requires that G2 on a -3 curve has a single fundamental hypermultiplet, which is a real representation. And so it has a USP2 group rotating it, which is a classical flavor. So you can do this now for any curve configuration that you're handed. Okay. So now I need to tell you something about how to compute the anomalies of these 60 superconformal field theories, and that will give us enough information to be able to compute the 4D central charges after compactifying. Okay, so the 60 anomaly polynomial is an 8 form written in terms of the characteristic classes of the various symmetry algebras of the theory. So for example, here, P1 T² P2, these are gravitational anomalies. There's an SU2R symmetry of the theory. This is a mixed R symmetry gravity anomaly, an R symmetry anomaly. And then there are a bunch of global symmetries or flavor symmetries. And these are TRF A². So A runs over all the flavor symmetries of the theory.
Sorry, so could you explain the notation? So T is the tangent bundle, R is the R symmetry bundle.
That's absolutely right. Yes, T is
what
the tangent
the FA
bundle.
or so what are the U1s or something? No. What are
they're the non-abelian flavor symmetries. Yeah. So indeed, there's sort of a question there, which is that you might ask why I don't at any point consider U1s. You could have asked on the classical flavor slide, for example, that I said that if you have a complex representation, the flavor group is SUN instead of UN. So one reason is that U1s are often broken by ABJ type anomalies. so one can also work through that, but in what we did, we only compared the non-abelian flavor symmetries. So that's the only ones I want to talk about today. Okay. So the anomaly polynomial I8, it can be computed from the geometric data, which is just the curves and the algebras, following some papers from around the 2015 time. However, we had to actually add some extra input for theories which may not have a geometric realization of their flavor symmetries, which I will explain in just a moment. So the anomaly polynomial can be split into two parts, something called a one-loop part, and then a Green-Schwarz term. So the one-loop part comes from essentially when you go onto the tensor branch, you have a bunch of multiplets floating around, and each of those multiplets contributes to the anomaly in some typical way. So if you have a tensor multiplet, it contains a self-dual 2 form, a self-dual 2 form is anomalous, and so on. And then the Green-Schwarz anomaly comes from the fact that you have tensionful strings, essentially, that come from D3 branes wrapping these finite volume curves. Okay, so let's just quickly walk through how to compute these two objects. So to compute the one loop anomaly, you need to know the contribution from each individual multiplet, which may appear on the tensor branch. So you have sort of, first of all, you have the 3 or 4, if you want, relatively ordinary multiplets, a tensor multiplet, a vector multiplet, a hypermultiplet. They're pretty standard. You can also have a 2, 0 tensor multiplet. Okay, that sounds fine. And you can also have E strings. So you might say, well, an E string is a strongly coupled CFT. What's it doing in the one loop contribution? But we can include it there. And so we do.
So I don't know too much about that. So is that, do you just get that from the 8 form of the M5 brane?
From the 2, 0, from the E string.
Oh, the E string,
yes,
the E string.
Yeah. So there's a paper by this paper here, Mori, Shimizu, Tachikawa. They essentially say it's an M5 brane probing an M9 wall, and then they do an inflow analysis and compute it. Okay.
So it's not just the 8 form you would associate with a single M5 brane wrapping something?
No, it's not. Okay. So now you have a little algorithm, which I certainly don't expect you to read, but it's algorithmic, which is great. For each curve that has a gauge algebra, you include a contribution of a tensor multiplet. For every gauge algebra, you include a vector multiplet. That seems pretty obvious. For every hypermultiplet, you include the contribution of a hypermultiplet, and so on. And then for each E string, you include a copy of the contribution of the E string. And then minus 2 curves with no algebra, you include essentially a copy of the 2, 0 tensor multiplet, because that's what they correspond to if you take just a minus 2 curve. Point I just want to emphasize is you can compute it sort of very algorithmically once you have the basic elements and you have the curve configuration. So here's our old example, 1, 2, 2, 3, 1, 3. With its flavor symmetries. And the one loop anomaly is just this tremendous creature. That's not too bad. Of course, this object will have gauge anomalies or mixed gauge and some other symmetry group anomaly, mixed gauge gravity, mixed gauge flavor, whatever. And having these gauge anomalies in the CFT will render the theory inconsistent under these gauge transformations, assuming the flavor symmetries exist, etc., which we always assume. And these gauge anomalies are cancelled through the Green-Schwarz term. So the Green-Schwarz term is essentially, it factorizes, it's a square. And it's written in terms of this quantity I. There's one of these i's for each compact curve in this theory, and this matrix here is just the intersection matrix of the compact curves. And in this paper by Omori, Shimizu, Tachikawa, and Yonakura, they explained sort of the origin of these coefficients. And some of them, like this yi, are a bit, one needs to take some care. in its definition. This is just the intersection matrix of the compact curves. And this is just essentially, it's roughly the self-intersection. And this object here is coming from, you have I, which is a gauge index, and A, which is a flavor index. So this is something which contributes to the mixed gauge flavor anomaly. So how do we determine what this coefficient B is? So one way of doing this, and the way which has sort of typically been done in examples, is that typically you have a geometry where the flavor symmetry is actually there. So for example, in our 131 with the SU3 in the middle, our old favorite example, the two E6 flavor symmetries, you can see them in the geometry when you write it down. So you know that the intersection number between the curves that contain those flavor symmetries and the compact curves, you know that that is 1. And so this object B in that case is just 1. However, you can't always construct a geometry with an intersection that includes the global symmetries. And so what we do is we just try and fix it by requiring mixed gauge flavor anomaly cancellation. So for example, you actually have to cancel these mixed gauge flavor anomalies in a 60 SCFT, which was originally only assumed or postulated in the paper of the authors I just listed previously. There was a recent proof that you require this in a paper by Cordova, Dumitrescu, and Intriligator. So if you do require this, then we find that this coefficient must be either, if it's classical flavor, it essentially has to be proportional to some kind of group theory coefficients, that's these AR. And if it's E-string flavor, it must be the embedding index. So you remember earlier, I told you that there was this funny SU2 with embedding index 8. Well, that 8 is very important here because you only cancel the gauge anomalies if this coefficient BIA is in fact 8. Okay. So I think I've now told you enough about 60 SCFTs to be able to start throwing some results at you. So yes, so now I'm going to wake everyone up. This talk was about 61,0, compactify on T2. You get some 40n equals 2 theories, and are these theories also having some realization inside of class S? And the results that we find is that each class S tinker toy, where one of the punctures is a simple puncture, can be realized as a 60 n equals 1,0 superconformal field theory compactified on T2. So I think, so first of all, I just need to quote one result, which is that once I've worked out the anomaly polynomial, the 4D central charges and the 4D flavor central charges are just given as linear combinations of the coefficients of the anomaly polynomial. So for example, you see beta appears here in the number of vectors and number of hypers, and beta is just the Toft coefficient of the mixed R symmetry gravitational anomaly. So this is something that was worked out in this paper of Omori, Shimizu, Tachikawa, and Yonakura. And it relies on this important assumption that the theory is, the 6D theory is what they call very Higgsable. In our case, every theory that we will consider will be very Higgsable, so we don't have to worry about this theorem. But if you want to start matching other 6D theories on T2, you have to maybe start worrying about this condition. So let me just jump right to the results. So a class S theory of type E6, compactified on a sphere with 3 punctures, that's a fixture. One of the punctures is simple, so I'm not going to bother writing it. So this is the case with 2 full punctures. This is the full puncture and some other kind of puncture. So the labeling here is the Balacarta labels for the punctures. I don't expect sort of you to understand the details here. This is just, these are different 3 puncture spheres, can be parameterized like this if you have one simple puncture. And these are 60 SCFTs parameterized in our usual notation as curves and algebras. And we see that they have central charges are the same for both. And flavor symmetries and flavor symmetry levels are the same from either this point of view or from this point of view. So that gives us some motivation to claim that everything has a 60 1,0 parent, because this is all possible fixtures that you can write down for type E6, where one of the punctures is simple. Okay. And as I told you at the start, this example is already known. E6 conformal matter on T2 is the same as 2 full punctures and 1 simple puncture. But this we now extend to include all of these other theories. So you can consider sort of the relationships amongst different punctures. I'm
not hearing him.
Craig, you're muted.
So these are related to the fact, and I took this table again from this paper of Chalcatana, Dissler, and Trim. You have a puncture. Say I have punctures 0, A1, 2A1, and 3A1. And those punctures are associated to pole structures. So those pole structures are essentially their differentials, which have expansions in terms of Coulomb branch parameters. And you can see that the pole structure changes. So here the 11 goes down to 10. Here the second 8 here goes down to 7. And here the 7 goes to 6. So those are what happen when you lose Coulomb branch parameters. Okay. So you can now draw this. So these are all the theories that I listed in the table. And when I draw a red line, what that means is that those two theories are connected on one hand from the class S point of view, meaning I have a Coulomb branch deformation that changes the poles such that I go from CFT1 to CFT2. But also in the 6-dimensional 1,0 point of view, these two theories are related by a 6-dimensional Higgs branch deformation. So we find that the structure that interrelates all of these theories is identical in 6D and 4D.
Craig, in 4D, for these flows, you give Fs to some Higgs branch operators, right? Not Coulomb branch. What do you mean by Coulomb branch?
Good. Yeah. So I'm calling it these because I take a coefficient, which is like I take a Coulomb branch parameter, which appears as a coefficient and an expansion of a differential. Mm-hmm. And then I fix that to be some value, such that I fix that to be 0 actually, such that I no longer have a pole there.
But this happens because of Higgsing when you give this Fs, right?
So indeed. So if you look, for example, you can see, where did I show the table? So this corresponds to Higgsing the flavor symmetry. So you have E6 24 here, and when you do this transformation of this puncture, you get SU6 18, which is the SU6 subalgebra of that flavor symmetry. Yeah, precisely. And you see this sort of continuing down. Okay, so that was sort of a limited set of examples. There were about 10 there. This is what happens if you start with the 2,0 theory of type E7. You get a lot more theories, you get about 50. And again, you find exactly the same thing for each fixture with 2 arbitrary punctures and 1 simple puncture. You have some 6D theory that when you compactify it on a T2, you get a theory with the same central charges, same flavor symmetry, same flavor levels.
Is the 6D theory unique, giving you this property?
Yes. So in this case, it is. I don't know of a reason why it should be unique in general. For example, I could imagine that there is some 4D theories which have multiple 6D theories. In some cases, yeah, and in every case, I know it's unique. Mm-hmm. But I don't know a real good principle for that to happen. So this is then the tree of, okay, I'm very sorry about this. There's a guy waving outside my window parcel. I will be back in 1 second. Okay, I'm sorry about that. He was waving at me. So you have E7 2,0 theory, compactified on a punctured Riemann surface. That's a sphere with 3 punctures. And those, again, the relationships amongst the punctures match exactly to the Higgs branch deformations or complex structure deformations amongst the 61,0 SCFTs. So you see this matching on the full sort of structure. Okay, so we can do the same thing for E8. I'm not going to draw the pictures or the tables here because they're huge. There are about 300 theories in those class of things. And in all cases, we match the central charges, the flavor symmetry groups, and the flows amongst the 40 and 60 points of view. So different perspectives on these theories can be useful. And one example of that is the following. I told you at the very start that the flavor symmetry group from the class S point of view can be enhanced. It's at least the flavor symmetry group of each puncture, the product of those, but it can be larger. And the way to tell that it's larger is you compute something called the Hall-Littlewood index, and you look to see if the characters of the representations recombine into a larger algebra. This can be rather tedious. And one thing which is particularly nice is that the global symmetry group, the enhanced global symmetry group, is manifest from the 61,0 point of view. So you gain something from that point of view. Okay, so since I am now at time, let me just conclude. So we found some significant overlap between 2,0 compactified on 3 punctured spheres and 61,0 compactified on T2. And we found that overlap sort of extended to the structure of the moduli space. I just want to make one remark, which is that we use this correspondence. We actually can use that to sort of reverse engineer some more information that's difficult about the 60 classification. So I raised this question of the flavor symmetries and whether they can be realized in the geometry. Well, those cases where the flavor symmetry is unclear from the geometry in 60 is a small fraction of the cases we consider. It's 3 or 4% of these 300 odd theories. So if we assume that the correspondence is in fact true, which means that the flavor symmetries that you would expect are really honestly there, even though we don't see them as in the geometry, this gives us a prediction for where they might be hidden in the geometry. So that's something where it kind of feeds back into understanding the geometric classification of 6D. Okay, and let me give a brief outlook. So one question you might ask yourself is, can the S2 or the Seiberg-Witten curve or something be observed in the mirror geometry to the non-compact Calabi-Yau? So you have the F-theory geometry with its curves and algebras. And what you would maybe expect is that if you take the mirror Calabi-Yau, then you might see the Seiberg-Witten curve or the 3-punctured sphere or something in this geometry. So this is what happened in the cases in the cases that I listed at the very start in this paper by Dozotto, Vaffa, and Shi, where they saw that for the plane conformal matter theories. And then you can ask about other 4D n equals 2 SCFTs. What about general G and N? We had that question during the talk, but I think that's sort of a very nice question, is can you start gluing these together and construct more complicated Riemann surfaces? Is there overlap there? And what about other classes of 4D n equals 2 SCFTs? So there is this proposal or principle which has recently sort of been put forward by Argyros and Martoni, building on older work with their other collaborators, where they classify using special Kähler geometry of the Coulomb branch. Can something like that be related to or usefully explored through this 1,0 origin? Yeah, so I think there are sort of plenty of interesting questions, and I could go on, but I think I'm out of time, so I will just say thank you for your attention, and I hope you can finish this seminar series having heard something somewhat interesting. Thank you.
Thank the speaker. If there are any questions, please just go ahead and unmute yourself.
So you said it very quickly, but I just want to confirm that I heard right. So, I mean, an obvious question is what about the gluing of two full punctures. So you don't have an analog of that in the 1-0 point viewpoint?
No, we do not.
So let's see, is it possible to say what a puncture corresponds to in the geometry, in the Coulomb? Does that even make sense, that question?
So good. So I will give you some speculations for why I don't think there is such a straightforward way of talking about the punctures on the other side of the on the 1,0 side. So the punctures affect the anomalies. Essentially, for every puncture, you add some fixed contribution. So on the 1,0 side, you don't have a notion of punctures, but you have a notion of adding collections of curves on the left and right of the quiver, or of the curve configuration. However, when you add on the left and the right, the anomaly polynomial is affected essentially by the length of the quiver, so the number of curves. So it doesn't grow just like some finite piece for each quiver, but it grows for each puncture, it grows for each kind of thing you add, it grows like the length of the quiver itself. So you see this very different scaling behavior amongst the kind of operations that you're doing on each side.
Okay, thanks. And so, so do you have any examples other than the three punctured spheres with one simple puncture? I'd be particularly interested in n equals 2 star, for example, even for SU2.
Okay, I have a lot of examples. However, the examples start getting pretty high. Like, so for example, there are a lot of examples where you take some 61,0 put on T2 and then compare that to something like a 6 punctured sphere. However, at that point, I can give you, 20, 50, 100 examples very easily, but I don't know whether that's now coincidence that you're dealing with central charges at large numbers or whether there's some structure there. Certainly, I haven't found another place where the structure, the relations amongst the moduli space on both sides is found.
But when you say you mean the conformal so a 6 punctured sphere, right, has a 3-dimensional conformal manifold. You can match that on the 1-0 side?
So at that point, I'm just matching NH and NV. At that point, I don't think it makes sense. The flavor symmetries don't match, but you probably wouldn't expect them to.
I was trying to, can you see the dimension of the conformal manifold from the 1-0 side?
I don't know how to do that. I think is still an open question. I don't know how to do that.
I think the answer is yes from the geometry in principle, that you could compute the dimension of the complex structure moduli space at the Coulomb. But I'm not sure it's been done.
Yeah, yeah.
But David, you should somehow be getting a Teichler space out of that.
Well, I know
that's right, but we're talking about the dimension right now.
Yeah, even the dimension. I mean, so one of the interesting features of the M0n bars, which are the conformal manifolds of punctured spheres, is that they're all smooth complex varieties.
Yeah.
Which is kind of would be an interesting feature to see from the Calabi-Yau complex structure moduli space point of view.
Yeah. So I played a little bit with trying to extract these quantities from the 6D theory. So based on saying if it's going to be dual to this particular class S theory, which it has the same potential charges as it, and that class S theory has a particular dimension of the conformal manifold, how do you sort of see that from the other side, but I couldn't find anything in the, like, just in the curve configuration. Maybe, as Dave says, you have to go to the full Calabi-Yau and do something more complicated, but just from the curve configuration, it does not appear obvious.
I mean, once you have the curve configuration, you can essentially figure out what the Weierstrass coefficients are in the family of elliptic curves. And, you know, each of those will be some polynomial and some variables. We can count the number of those. So that's why I'm saying that in principle, one ought to be able to compute it. I'm not sure if it's really been done, but in principle.
Yeah, I agree. In principle, it should be hidden in the, or maybe not hidden, but should be in the geometry. But I don't know how to extract it, sort of, other than as you say.
So there is. I have a comment about that. So together with Coulomb, Gabi, and Hitchell, we looked on compactifications with flux on Torre of some 1,0 theories. And there also, like experimentally, since we understand some of the classes of 4D theories, there are actually maps between, say, compactifying D-type 1,0 theories coming from M5 branes probing D-type singularities on, say, Torre with flux. This maps to A-type, like M5 branes probing A-type singularities on spheres with punctures. And you have this Torre, and you have these spheres with a lot of punctures, and there are complex, there are conformal manifolds in the both on both sides, and you can match them. Like on one side, you have, for example, exact marginal deformations coming from flat connections for the global symmetries. Okay. Not from the complex structure moduli, but for flat connections. And on the other side, this comes from punctures, from complex structure moduli. So there can be such a mapping in principle.
Yeah, I agree.
Hi, Craig.
Hi.
Thanks for the very nice talk. I have a question. So for the Hasse diagram you showed in the end, where you took E-type conformal matters and turn on different nilpotent orbits of two punctures, I wonder how general that is. And like, for example, if we look at the E6 conformal matter case, I wonder, can you put two conformal matters and put a 6 curve in between and still do the same trick?
Good question.
Something like
well, okay, so if you take the rank K conformal matter, this just means you take sort of conformal matter, and you glue it together by a 6 curve, and you iterate this procedure K times. So these things in this paper I cited at the end by Del Zotto, Vafa, and Shi, they study these things, and these things are dual to an and let's see if I get this right. Okay, I'm not going to get it right. It's dual to a sphere with roughly K punctures, roughly K simple punctures, and 2 full punctures. Maybe 2 full punctures or something, I'm not sure. So these theories are not very Higgsable, which makes them a little bit more detailed to study from the 6D side. That's one other thing that is known, is that rank K GG conformal matter is the 2,0 theory of type G on a sphere with 2 full and K simple punctures.
I see. So the point I asked this is that in another paper I had with Hassler, Heckman, Hochschild, and Rudelius, we got some results of very similar mathematical structure at this, but it's purely in 6D. So the nilpotent orbits there are interpreted as nilpotent webs inside the 6D flavor symmetries. And then we did that via the method of like string junctions and propagating D-term constraint. We got similar results, but for the D-type, where we can do rank K D-type conformal matter, but we sort of count like go to the E-type. And that's why I'm very curious about this.
Yeah, so yeah, thank you for the very sort of interesting question. So I think what you expect to find, if I'm remembering the right paper, then there you're finding sort of the Higgs branch deformations on the 6D 1,0 side are governed by choosing nilpotent orbits inside of E6 for E6 conformal matter, say.
Mm-hmm.
And since the structure on the 4D side, the structure of the punctures is also chosen by choosing nilpotent orbits of the 2,0 starting point, it's not surprising to me that you see something very similar to these kind of diagrams. And it may in fact be exactly the same thing, because in these diagrams, the 60 part of it is looking at Higgs branch deformations, which I think you may be saying is precisely what you looked at there. So it may be more than just similar. They may in fact be to that structure, although we haven't thought about it in terms of these nilpotent the nilpotent orbits. We just did the deformations by hand and worked out this tree.
Yeah, indeed, I highly agree. And I think by cross-matching our two perspectives, we could probably both reach the corners that we previously couldn't.
Yeah, I think that would be interesting. Yeah.
Okay, thanks. Cool.
May I ask a question?
Yeah.
So sometimes in class S, it happens that a given three-puncture sphere corresponds to an SCFT, which is actually the product of two different SCFTs. Like it happens many times with the Minahan-Meshansky theories. And I believe there are examples also in the class of theories that you are considering, because for example, if I remember correctly, in E6 class S, you can have one minimal puncture, one maximal, and one puncture I don't remember. And this should give two copies of E8 in a Minahan-Meshansky.
Yes.
Do you see this factorization in the 1,0 side?
So we do. So for example, if you can see the screen, you see this theory down here, which I've written with the two bars, 1 double bar 1, you see it down here. So that theory is in 60, that's two copies of the E string that are disconnected. And when you compactify it on a T2, that gives you two copies of the E8 Minahan-Meshansky theory. And actually one particular upside of this is that, well, so Jacques had a paper with some of his collaborators recently studying when a class S theory is a product theory.
Yes.
And it involved computing the superconformal index, and they gave several sort of heuristic ways of determining it as well.
We also give
and one thing that
other than the index, but okay.
Yes, sorry, indeed. So one thing that we find is that the 60 theory as a product corresponds to the cases where the class S theories are a product. And using this, we could kind of predict some class S theories that are products that, at least to our knowledge, were not previously written down as products.
Yeah, this is very nice. I think it's another little piece of evidence other than the central charges and so on. Like you can recover the right product structures from the 1,0 side.
Yeah, you certainly, you just read them off immediately because it's a product in 60 too.
I see. Thank you very much.
But is this prediction, or you just, the way you map these class S constructions and 1,0 construction is not systematic, right? You just go over all the possible class S theories and find the 1,0 theories, or is there an algorithm to?
No. So one way of saying this algorithmically is that you know that one simple and two full punctures corresponds to
and then
conformal matter, and then do a Higgs branch deformation, do a deformation of the punctures, and just continue that procedure. And you see that the central charges match at every step.
Okay.
Craig, I have another question. So it seems you're just taking conformal matter theories and reducing them. So TOEs, I guess how was just implying, you have some sort of hitching system that governs those T-brane structures, right? So if you take that hitching system that governs those T-brane structures and you reduce it on the torus, do you think you could land exactly on the hitching system that actually governs the class S structure, which itself is what helps you classify these punctures?
So I would like to be able to say, yes, we can see immediately in the geometry on the F theory or 1,0 side.
Yeah.
but I don't know how to do that. I don't know if it's even should be possible. The algorithm to do that might be as horrible as write down the geometry, then construct the mirror geometry, and then read it off, which is, of course, not particularly helpful.
But both of them seem to be controlled by some codimension to some hyperkähler 4D space where these hitching systems live, right? So shouldn't it be just a question of in the 6D, you have to pick some extra torus and then somehow reduce on this and then get the same hitching system?
That may, so I don't immediately see where it comes from. I'd have to think about it, but
another question. So here you have 3 punctured spheres where one is simple, and so you have this linear structure. But you can also have a 2 puncture sphere where one is like, let's say, maximal and another is an irregular puncture. Can you see irregular puncture from 6D?
So we have examples of 3 punctured spheres that contain irregular punctures. I haven't looked for the 2 punctured ones, like these ones that have been written down, for example, by, I can't remember the particular name of these kinds of theories, Giacomelli et al. Have studied them.
Do you have a generic type of irregular puncture, or do you have a specific class of them?
So we were looking at just the ones from just colliding 2 regular punctures that allow you to have a 3 puncture sphere with it on it that's a consistent theory. So there we just took the list of 3 puncture spheres with irregular punctures that Jacques and collaborators have published over the last several years.
Okay. Thank you. Are there
wait, question in the chat. Are there 4D examples from the 6D that do not have class S descriptions? Yes. Yes. So I mean, it's sometimes hard to say that something definitively does not have a class S description. So what I can say is things like there are certainly 6D SCFTs that do not have class S descriptions of where the 2,0 theory is of exceptional type and you use only regular punctures or so on. So I can say words like this. It appears that there is probably a lot of theories which are not of type class S. And this you also see from other studies of 4D n equals 2, like work by Argyros et al., where they have a lot of 4D n equals 2 theories that don't necessarily have a class S description.
Can you prove that these are not class S, or you just don't know what the class S theory could be?
I think one of the problems is that class S has sort of so many bells and whistles that you have to be careful to exclude everything. Irregular punctures, as Ibu was just talking about, and you can sort of play around with it, and you would have to rule out a lot of things that we haven't done.
But even with only regular punctures, just so do you have an example that you can argue that no class S theory on any genus, but only with regular punctures can reproduce it?
So I have some arguments which are, so if you write down something like an n-punctured sphere or an n-punctured arbitrary genus thing, you know that theory may also contain sort of a free sector. So sometimes you can show that there is a 6D 1,0 theory that when you compactify it on a T2, its central charge NH is larger than any other class S theory with regular punctures. So this indicates that that theory cannot be realized as a class S theory. I don't have a sophisticated way of saying this though, other than that sort of these theories have low enough central charges that you can check.
But it can decouple into CFTs like a product in principle. Can you rule out such things?
No, we can't rule out such things.
Okay.
You would expect to see that from the 6D point of view if it replicates it, but you could imagine it being inside of some ridiculous thing which just splits it off as a little bubble. So that right. I don't know how to rule out.
May I add a comment or a question on this this thing? So maybe it's a very naive question, but take a for the n equal to 2 theory that is a quiver, but not a linear quiver. So you have a node that connects with like different nodes, like some E6 shaped. Does this have a class S description? Because typically gauge should be tube, and tube should be attached just to two things, but you can make a for the n equal to 2 quiver with one gauge node attached to more than two other nodes. So is it known what is the class S description for something like that?
So I don't know any example of something like that, and it's somewhat hard to imagine how to construct an example of something like that because the 61,0 theories are themselves inherently linear. So they look like very long linear quivers. And so it's sort of, you have something on the left and you have something on the right. And roughly what's on the left and the right maps to the choice of punctures in the examples where there's overlap. And you never really have more options than this. There are some accidental things where you can write down something like that and then just scan over all possible compactifications of 1,0 and you say, well, there's some central charges that overlap. But I wouldn't go beyond saying that that could be just a coincidence.
Well, I've heard the following claim, which is related to this, that if you take the E8 diagram with its Mackay labels on the nodes and multiply them all by n, okay, now you get a quiver gauge theory.
Yes.
And so Yuji and Oscar have claimed to me that this cannot possibly be of class S because of something to do with the branch, and I can't give you the argument because I never understood it. But they said it something about it was something about either the reduction to 3 dimensions of the Higgs branch. Maybe somebody here on the Zoom session knows the argument. Can give it.
So this is the E8 shaped quiver?
Yeah. So I mean, the claim I understand the claim. I just don't understand how to prove it. The claim is that you take an E8 diagram, and then there are these famous Mackay numbers that you could put on the nodes, right? So that the average of the labels around each node is the value at the node. It appears in the Mackay correspondence, for example. So then you multiply those numbers by n, okay, to get some of gauge groups at the nodes. And gauge theory.
Yeah.
Okay. So the claim is that that can't possibly be of class S.
Yeah.
And that's a claim that has been made to me by Yuji and by Oscar.
Well, I could make that claim too.
Okay, maybe Jacques, you can supply the argument.
Well, so in class S, what you have is well. So let me say that a similar argument might have held for you might have tried to make. In fact, people did make a similar argument for affine quivers of type D. And it turns out those are in class S. But in order to sort of understand why,
well, that undermines the credibility of the argument, doesn't it?
Oh, I know, but you have, when you understand sort of the escape hatch that affine quivers of type D manage to find, you can sort of convince yourself that affine quivers of type E don't. So the idea is that in quiver gauge theories, you have a bunch of gauge groups and bifundamental matter. In theories of class S, what you have are gauge group. So you can also represent them by graphs, but the roles of edges and nodes are reversed. So edges are gauge groups, and vertices are some kind of matter, right? So you can have vertices that are charged under up to 3 gauge groups, but each gauge group has only sort of 2 types of matter that are charged under it, right? Because each edge, ends on 2 different nodes, right? So you would have expected that you could only get linear quivers out of that.
That was the argument Federico was just giving.
Right. But now the point is in affine type D, right? You see that from the quiver point of view, there's a gauge group which has charged 3 different types of 3 different representations of charged matter, right? Because there are 3 edges that end on that node of the quiver.
Yes.
Right.
Mm-hmm.
And what happens in the twisted type A to n minus 1, 2n minus 1 theories is that you can get non-simple gauge groups, in fact, product gauge groups, SUN cross SUN. And so therefore, and so the ends of the quiver
the
are
SUN
actually
wins
sort of
SUN from
special.
the class S side.
I'm explaining from the class S how type affine type D escapes this. And the difference with affine type E is that that sort of phenomenon where you have 3 sets of bifundamental matter which are charged under some given node of the quiver happens not at the end of the quiver where we have this clever mechanism from the twisted theories, but at the next node over, sort of in the middle of the quiver.
Yes.
And that I don't know how to do.
I see.
Okay, I have to say I don't really find this argument incredibly convincing. I mean, the claim might be right.
Well, I mean, the claim is only about what I know how to do.
Just because we don't know how to do it doesn't mean it can't be done.
So I know a way to obtain.
There can be funny
equivalences
equivalences too.
Right. So there is a way to obtain these affine quivers, but starting from E-type conformal matter on a torus with flux, you can get both E6 affine, E7, and E8. That can be done. But I don't know, from that perspective, the enhancement to n equal 2 is completely mysterious because the construction supposed to give you n equal 1, and it gives you these quivers plus some free fields. Okay, but
Shlomo, maybe there's a limit of some parameters where there's an enhanced supersymmetry.
Yeah, of course. Well, I don't know how to explain it, but there is like you have a general algorithm how to combine these tori theories from blocks, and the blocks are n equal 1 supersymmetric. Once you build a particular theory, you see that it is n equal 2. You get exactly these quiver theories. But why you get an equal, like what is the geometric reason for the enhancement? I don't know. That's the claim.
I mean, there are other examples of this too, right? Where you can have even simpler n equal to 1 quiver, n equal to 1 theories, which have some quiver-like structure, where it's not linear in any meaningful way, but it can describe things that would be n equal to 1 punctures. But then this, if you take those objects, you can glue them in some interesting way, and you can have an interesting n equal to 2 enhancement in the low energy. So this is the Mariyoshi song sort of enhancement.
That's right.
Which gives you things like Argyll-Douglas theories. So certainly we know how to engineer n equal to 1 type stuff, linear quivers, which are in class S, but flow to n equal to 2 theories.
Yeah.
And this would be sort of an exception to the sort of argument that Jacques was just giving.
Yes, but in this way, you manifestly go to n equal 1 length. You kind of go out of 8 supercharges, and then you increase the number of things you can do. So.
Yeah. So now there are many examples of that kind. So it's hard to just say to rule things out not in class S in that way.
Yeah. Okay.
There aren't any more questions. Let's thank the speaker one more time, and we can stop the recording.